Hello, everyone, and welcome to We Meet at Digital Days. My name is Lisa Richter, and I will moderate this presentation. We are very pleased that you took the time to participate in our virtual conference. The topic of this presentation is how to select a suitable EMC cable ferrite according to parameters and application. Our speaker is Igor Rodriguez. He will hold a presentation and will answer your questions. So, before we start, I just want to mention one thing. You will be muted during the presentation. This means that you cannot ask questions via microphone during the presentations. Nevertheless, you have the opportunity to ask questions during the presentation at any time via the chat function. You will find the chat function in the control panel. This presentation will be about 30 minutes long. The chat question will be answered in a Q&A session following the webinar. There are 5 to 10 minutes in addition scheduled for this. If we are unable to answer all of your questions within this time, we will answer them via email afterwards. If you still have any other questions left, just mail us at exhibition@we-online.com. We will try to answer all the questions promptly. At the end of the webinar, you'll be asked to participate in a feedback survey. We would be pleased if you take the time to fill out a survey and help us to improve our event. You will receive the link to the presentation in the next few days. The recording will be available at our website shortly. So now I will hand over the presentation to Igor. And I wish you an exciting presentation.
Thank you, Lisa. Good afternoon to everybody that's present here on this cold winter afternoon. My name is Igor Daventura Rodriguez. I am Field Applications Engineer for Würth Elektronik in the UK. And it is a pleasure being here with you on this webinar session where we'll be discussing about cable ferrite selection. Our agenda basically will be the basics of ferrites. Then we'll be talking about the parameters. We'll get to know a little bit better the parameters so we can do a good selection of cable ferrites. And finally, we'll see the solutions that we've got available on this field of the cable ferrites. And at last, we'll see the usage of RedExpert when we need to select a cable ferrite. So starting with the basics, the first question is, what is a cable ferrite? And here on the screen, you can see that the ferrite, the cable ferrite, will be just a piece of ferromagnetic material that will or not have a plastic enclosure, and it will go around a wire. It's got a hole where you will pass the wire through. And it's an EMC filtering component. And what does it do? Basically, it will act as a low pass filter. So it will block any high frequency signals that you will have on your line, and you can utilize it both as a differential mode noise filter or a common mode noise filter. It all depends, for example, if you put both of the conductors inside of it or just one. If you are utilizing it, if you strip this cable and you leave just one of these two conductors inside of this ferrite, it will act as a differential mode noise filter. If both are inside, then it will block common mode noise. And when do I use the cable ferrites? You will utilize cable ferrites whenever you need to filter, to attenuate noise. That can be, for example, harmonics, as we can see here in the screen, the peaks that are exceeding our maximum permissible level. So in general, these ferrites will be utilized in order to pass the EMC tests and to guarantee that your device will have a good functioning and will not interfere with other devices. We've seen earlier today about SMT ferrites. And one of the main differences between SMT ferrites and cable ferrites will be that this will be a retrofit solution instead. So with the cable ferrites, you don't have to redesign your product essentially. So this will be on that case where you don't have either time to redesign, or the investment to redesign is not going to be worth, or you actually cannot redesign the other blocks for any other given reason. Then you can sort out your problem with a cable ferrite. And it will help you against both conducted and radiated, both emissions and immunity. And they work based on the magnetic field principles. So whenever you have a magnetic field that is flowing through a conductor, it will generate, as you can see in the screen here in blue, magnetic field lines. And the ferrite material will grab this magnetic field and will convert it into heat. This magnetic field, of course, will be related to the noise current that you're going to have on your cable. This is also known as impedance. And for a better understanding, we will remember some basic concepts of the magnetic field, which are intensity, flux, and permeability. And then after that, we'll talk a little bit about magnetostriction. So whenever you have a magnetic field that is flowing through a conductor, you will have your current flowing through the conductor, and it will generate a magnetic field. And we commonly refer to this with the right-hand rule, where your thumb is the current and your fingers are the magnetic field lines. So you can even visualize this model if you're looking at it like from the top. If you put some metal filings on a smooth surface, and then when you run the current through the wire, you will see the metal filings organizing themselves according to the magnetic field lines. Then when we talk about magnetic field, we talk also about magnetic field intensity. The intensity of the magnetic field doesn't depend on the material that you've got. It will be the same regardless if it's on the air or on a ferrite material. It will depend basically just of the radius, so the distance between the emitting point and where you are measuring. Okay, so in this example here, we have a ferrite with a cable that has got a current, and of course, it generates a magnetic field. So nevertheless, we have something that we describe as B, which is the magnetic flux density, and B will be different inside or outside your ferromagnetic material. Okay, because the ferromagnetic materials, they will concentrate the magnetic field lines, as we can see on the top of your screen right now. Instead of like non-ferromagnetic materials such as the air or ceramic, a piece of plastic, a piece of glass, that they will be literally transparent materials for your magnetic field. Okay, so the ferromagnetic material will present an easier path for your magnetic field lines. Okay. Then we have something that we call mu, which is the relative magnetic permeability of any material. It's relative because it's relative to the air. If we measure, of course, the permeability of the air and compare it to the air itself, it will be 1, and it will be constant. Nevertheless, when you go to other materials, especially the ferromagnetic ones, you will measure a different value. And this value will be dependent on various things, such as the material, the frequency, the temperature, the current, and also the pressure. So this is the theoretical definition of a relative permeability. It describes the ability to concentrate the magnetic flux inside the core material. So this is one of the key parameters for your ferrite. So if you analyze your ferrite material, you'll see that it will be consisting on various micromagnets, which we call magnetic domains. So these little micromagnets that you've got inside your ferrite, they are unsorted, they are not organized, they are on different orientations. And once you apply a magnetic field on them, they will align on the same direction. And this is the process that will basically cause the loss of energy of your noise, so the attenuation of your noise. On the other hand, when you grab a permanent magnet, exactly as the magnets that you've got on your fridge, and you see the micromagnets, the magnetic domains, they will be already all aligned. So there is nothing to do here. They're already aligned. If you apply more energy, it will do nothing to you. Okay, so we call this kind of material as hard magnetic material. Meanwhile, your ferrites will be using soft magnetic materials. Okay, so they can get organized once you have a magnetic flux on them, and they will get disorganized once that flux is over. Okay, and here are some examples of the typical μR values for some of the most common ferromagnetic materials that are utilized in order to make electronic components, such as iron powder or superflux that they've got between 50 and 150 of μR, nickel zinc that has got between 40 and 1500, and last but not least, manganese zinc that has got between 300 and 20,000. So quite a lot. Last concept on our little review is magnetostriction, which is basically an effect caused, as you can see by this animation here, that the magnets, the magnetic domains inside the material, when they are reorienting, when they are realigning, they will cause forces on that material which will change its shape and dimensions. So in order to do that, you can see here that we'll be having losses in the form of torque and friction. So basically, these are the factors that make ferrite to work dissipating. All right, so after knowing this, what is the cable ferrite that I should select? In order to select the correct cable ferrite, you have to be aware of all of the parameters that you've got for your ferrite. The first one is the impedance curve. The impedance curve will describe you what is the impedance that your ferrite will present on each point, on each frequency of your spectrum, right? So we divided this in 3 colored blocks, both blue, green, and yellow, which represent respectively the inductive part of the ferrite, so where the inductive behavior is more prominent, then where the resistive behavior is dominating, and then when the capacitive behavior is dominating. Okay, ideally a ferrite would be purely resistive across the whole spectrum, but there's no way of doing such because the component is not perfect. They have always parasitics. Okay? And one of the parasitics will be the capacitance. The capacitance will be always there, and the capacitance will shape that curve downwards. Okay, so and it will limit the frequency response of our ferrites. On the peak here, you have something that we call SRF, or self-resonant frequency. This is the point where the capacitance and the inductance that you have on the ferrite will be equal to each other. So they will cancel each other and you will have a purely resistive component. With a frequency response, one thing that you have to always look for is actually analyzing the curve, not only the data sheet, which gives you 1 point only of this curve or 2 points of this curve, right? Because not always the ferrite that shows these parameters here, the highest, will be the best for your case. Instead, always bear in mind what and where and how powerful are the peaks that you've got in your spectrum, and because this is what you want to fight against, right? It doesn't matter if I have a ferrite that will just attenuate this peak here a lot and it will not do anything to the other ones. I won't pass. So always have this critical thinking and this eagle-eye vision in order to analyze the whole problem and choose the most adequate ferrite in these terms. Okay, so always consider the attenuation that you need. The cable ferrites are mainly made out of these 3 different materials: manganese zinc for the lower frequencies, nickel zinc for the mid to high frequencies, and nickel zinc HF or nickel zinc high frequency for higher frequencies. Another parameter that is important, of course, is choosing the correct cable diameter or the width of the opening of your ferrite. Because if you have a thick cable, you cannot utilize these little tiny ferrites, of course. And in these terms, we go from 0.55 millimeters up to 33.4 millimeters for round wires, which are these big ferrites here. Okay, just to give you an idea, this one that I've got here is of 25 millimeters, if I'm not mistaken. Quite a big one, isn't it? So also we have ferrites, of course, for flat cables, and these will go to a cable width of up to 81.9 millimeters. So always make sure that the cable will fit inside the ferrite, and be mindful of the overall size for your solution. And always bear in mind that normally the bigger the ferrites, the more attenuation you're going to get, because you'll have more material. So once again, we have ferrites for round and flat cables. So you can choose your ferrite based on this. And we have different mounting styles. We will have the snap-on ferrites, which you can go ahead and, for example, you're on an EMC Lab and you cannot remove a cable, no problem. The cable will be there. You just clap the ferrites around that cable and the job is done. We will have split ferrites as well. And we have, of course, these clips that can help you to mount split ferrite, or you can use a heat shrink tube, for example, in order to fix it. And also we have the solid core ferrites. Temperature-wise, it's always important to observe that we have what we call the Curie temperature, which is a temperature where the ferrite will lose its magnetic properties, so it will not work anymore if you reach that temperature. And of course, you want to operate always below that temperature, and always consider that your components will have a certain self-heating, and you will have the ambient temperature. This will be the final temperature of your component. So always observe on the data sheet what's the maximum operating temperature and make sure you are within this specification. Positioning of the cable ferrites is important as well. We always suggest you having a distance between 20 and 50 millimeters, as you can see here on the screen, between your ferrite and the noise source or the block that's being affected by the noise. This will enhance the capabilities of the ferrite. So basically, if you put your ferrite too far away from your device, it will not work as intended, because that bit after the ferrite, between the ferrite and your device, it will act as an antenna. So possibly you can get some noise issues with it as well, especially if it's radiated. Okay. And of course, you cannot put it too close to your device, to the point that it will be like touching and rattling around here and risking to break or something. That's why we observe this little distance. Okay. Then common mode or differential mode. Did you know that you can utilize the Snap-on ferrites as a detective tool? Yes. How do you do that? Quite simple. You first of all place all the lines inside the ferrite as it is on the drawing here. You give it one turn or two, you choose. And then if you don't measure any attenuation on your spectrum analyzer, it means that this will be a differential mode noise. So then you'll have to split this cable and try one ferrite on each line. Else, if you have attenuation, then you're good to go. You have common mode noise and your ferrite will work this way for you. Okay. If none of these work, it means that this noise is not coming or getting inside on that specific cable. This can be really helpful on an EMC Lab. So now let's check our cable ferrite portfolio. And once again, I've listed here for you all of the ferrites that we've got available. So you can see various things here. We can see this red bars here that indicate what is the cable diameter that you can fit within that specific ferrite family. Also, the black bars here indicate which are the impedance ranges that we're going to have for each of these. Okay, and yeah, so you can go ahead and easily select your ferrites. We can see here that also we've got the division by style. So we have here the snap ferrites, which we have the Star Tech, the Star Ring, the Star Bueno, and the Star Gap. And the kind of material that is utilized on these ferrites: nickel zinc or nickel zinc high frequency in the case of the Star Gap. Then we have split core, solid core, and finally a split core here again. So these are for medium and high frequencies. If you need ferrites for low frequencies, you can utilize either StarTech LFS or AFB LFS that are made out of manganese zinc, and we have them in both styles, snap or solid core. And last but not least, you have ferrites for flat cables. Once again, with the cable width indicated here on the red bars and the impedances on the black bars. Okay, so you will have again snap, solid cores, and split cores. Also, we have some accessories such as the star clip, so you can fix your ferrite to a chassis or any other mechanical structure. All of the ferrites, they feature, at least the snap-ons, they feature this key that's called a We Star key in order to prevent unauthorized access, and you can easily open your ferrite. And you have what we call the FCAC, which is a fixation kit for flat cores on ribbon cables. All right, so now let's use RedExpert a little bit in order to select ferrite. You have the link here on this presentation that will be made available for you after we finish our event. That leads you to RedExpert. So within RedExpert, we can easily select and compare ferrites. You have even some really nice tools that will allow us to do selection really quickly in a precise manner. And for this, we prepared a little example to show you how to select a cable ferrite via RedExpert. Okay, so let's pretend we are at the EMC Lab and boom, there was an issue and we had a power line of a DC-DC converter. This is an industrial application and we have a spike at 80 megahertz that we want to attenuate on 25 dBs. Our cable diameter is 15 millimeters and we cannot disconnect the cable on both ends. And black color is preferred. Okay. Some comments here. Since we cannot disconnect the cable on both ends, we will have to consider snap ferrites. Okay. And we have the ferrites as standard on a light gray and also on black color, which is quite nice. But we also have them available in other colors if it's necessary. All right, so let's go there to RedExpert. Okay, if you type on Google or if you type redexpert.we-online.com, you will be on this very same page. If you're not registered, please register on RedExpert. It's free and you don't get any annoying emails, I promise. And we'll click here on products and we'll go here to ferrites for cable assembly in order to load the module that I was showing you on the presentation. So once we are here on this module, we can, as you can see the ferrites drawings here, the impedance curves for 1 and 2 turns. So it's quite nice and you can compare them. You can do loads of stuff with this. So we will go here to the system tool and we'll wait for it to load. Once we are here on the system tool, you remember that we said that it was a DC-DC converter. So I will use this slider in order to select here supply for voltage lines, VCC, 10 ohms. It will automatically set 10 ohms for me on Z in or in Z out. If you know the specific impedances, you can just manually type them here. So on our example, we want to attenuate 25 dBs at, apologies for my bad memory, 25 dBs, just a second, at 80 megahertz for a cable diameter of 15 millimeters. Okay, so let's put this 80 megahertz. Once I've entered all this information, RedExpert already calculated for me which ferrites can be useful for this scenario. And my cable diameter is 15 millimeters. Let's start with 15 millimeters exactly to see what we've got. Okay, so we've got 2 results. So if I compare both, I will see just the same curve because they are exactly the same ferrite, but the only thing that changes is the color. So with an S at the end, it means Schwarze, which is, sorry about my German, it's not the best, but it means black in German. So actually, this is the ferrite that we want. And as you could see, we selected the ferrite in what? A minute or 2. So this can be really useful for you. Okay. So back to the presentation. We reached the end of the presentation, and yeah, now we have a space for your questions here. So let's see. Let me see the questions that we've got here.
So thank you, Igor, for your interesting presentation, first of all.
Cheers.
So just let us take a look at the question part here. I can see one. Which effect could be observed at a Curie temperature? Can you give an information here?
Yeah. Well, basically, thank you for your question. And basically, what happens at the Curie temperature? Remember that we've got those micromagnets or device domains, the magnetic domains inside the ferrite. What happens with temperature with any material is that the particles will be vibrating more. They will be moving more and more and more. So what happens is that your magnetic domains are particles, are atoms as well. So they will be moving in a way that when you pass the magnetic flux through them, they won't take effect. They will not be able to all align beautifully together in order to create a higher μr. So this is what happens. The more temperature you have, the more agitation of the particles you have, and then they will not be able to align. It will be just a mess, a madness. So it's not going to work, just that. But after it cools down, it will restart working. There is a temperature much, much higher to which, if you reach it, but I'm talking about thousands of degrees. If you reach that, then the material will lose forever its magnetic capabilities.
Okay, thank you. So the next one, is it possible to use RedExpert to simulate an ESD discharge on the cable?
Not yet. We cannot use yet RedExpert in order to simulate ESD. But who knows in the future? RedExpert is a living thing. So more and more every day, every year, we are adding more and more new modules on RedExpert. So we'll take that in consideration, and I'll pass the suggestion to the RedExpert team in order to see if they can implement it. Thank you.
So hopefully in the future. So the next question, does it
have
any advantage?
Sorry.
No problem. Does it have any advantage to loop condition? We would move the cursor to 150 ohm for longer data lines.
Does it have any advantage to loop the cable?
Between two questions.
Yeah.
Sorry, there was one more.
No,
now it's a mix-up. So
no
the
problem,
question
no
is, does it have any advantage to loop the cable multiple times through the ferrite?
It can have. It can have. Basically, when you loop a cable on the ferrite, basically when you have a ferrite and you have a cable, you are wanting to create an inductance there. And when you have more turns, you will have more inductance. That's your advantage. But depending on the material of your ferrite, you will have another effect taking place as well. It's not that you will have more attenuation in your curve. It will just go up, and it will be stronger. It will go up eventually, but it can also shift towards higher frequencies. So if your problem is here on lower frequencies, perhaps it won't be good for you. So once again, we have to know what's the full spectrum, the full picture of the problem in order to determine if this is going to be good or not for you.
Okay, great. So the second question was, in RedExpert tool, we moved the cursor to 90 ohm for data lines, but in which condition we would move the cursor to 150 ohm for long data lines?
These are just relative values, really. These are just estimate values, because at the end of the day, most of the cases we don't know actually what's the precise value of impedance that you're going to have on Z in and Z out. And these values, they will of course affect the calculation that is done in order to determine the filter with your minimum impedance at a given frequency. But the criteria is like, well, I have a longer data line of, I don't know, 20, 30 meters, then I can say yes, it would be better like utilizing the 150 ohms here to have a better result. But it's like there's not like a hard rule to choose either 90 or 150, or you could type any values in between, really. It's just a reference more than anything.
Okay, great. So just thank you for answering the questions. If there are any other questions left, we will answer them via email afterwards. Thank you all for your attention, and I hope you enjoyed our presentation. The next presentation topic is, does size really matter? Design effects on crystal downsizing. So see you there and enjoy our digital days. Goodbye.
Bye.